All right. So today we will be talking about Bayes' theorem some more. I introduced this before. There's this idea of, not just in probability, but just in mathematics in general, sort of the bedrock of whatever the math category is, be it algebra or geometry or calculus, or in this case, probability, where the bedrock are axioms and definitions. So let me go up. Here are definitions. There's a definition of a probability space. A definition can be anything you want it to be. The world is yours. Just you're laying ground rules. You're letting other people know when you say this thing, what does it mean, and it's a blank canvas. But once you start laying down definitions, then they start to build up, and now we're talking about something. So for probability, this is the bedrock. Probability space. There's a set and a function. The set follows set theory. We've talked about sets. Set theory isn't so complicated. There's no repeats. I mean, you can have repeats, but you just ignore them if they exist. And order doesn't matter. And sets can intersect. That's where whatever sets have common elements, then their intersection are those elements that two different sets have in common. And then there's this function that is a part of the probability space, where the function takes as an input members of a set, elements of a set, and assigns them some number between 0 and 1. There's an extra thing where all of the numbers that this function maps to between 0 and 1, they all add up to the number 1. So this is bedrock stuff for probability. All right, so we have a definition here of a probability space. It's two things, a set and a function. Great. Probability space is doing something one time, and that's it. So you flip a coin. Great. Here, we're flipping a coin. There's the set, heads or tails. If it's a fair coin, then heads and tails each have an equal probability of 1/2. Because the coin is fair, it adds up to 1. This is describing the flipping of one coin, one time. You want to talk about flipping a coin 2 times, or 3 times, or more than once? Go for it. You can do that. But then you need to describe a new space. This coin probability space describes one coin flip one time. You want to flip the thing 2 times, 3 times, however many times. Then you make a joint probability space. You can start with the one flip, and then there's a way here to define a joint space, where maybe here we flip one coin, then we flip it again, and we flip it n times, and the probability of flipping, let's say, all heads is the probability of flipping heads on the first flip times the probability of flipping heads on the second flip times the probability on and on until the nth flip, the last flip. Now, this is going to be a very small probability for all heads, or for any particular sequence. All heads, all tails, half heads, half tails. But here, the half heads, half tails, which are going to be of a higher probability, is going to be the same small probability to flip this exact sequence of heads and tails. So I flip a coin 4 times. I get all heads. That happens with probability 1/16. I flip heads, heads, tails, tails. Exactly in that order. That's also 1/16. I flip heads, tails, heads, tails. In that exact order, also 1/16. I flip tails, tails, heads, heads. That exact order, still 1/16. Now, you can define an event, which is a subset of everything that can happen. So, if we're flipping a coin 4 times, maybe we want to think about the event of 2 heads, 2 tails. Then we can define the joint probability space, which again, this is a definition. You don't need to be creative. You don't need to be clever. You just build the thing according to the definition. So while the probability of heads, tails is the same as heads, 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 the event of 2 heads, 2 tails is a collection of events. That could be heads, heads, tails, tails. It could be heads, tails, heads, tails. It could be tails, tails, heads, heads. It could be, you work it out yourself. It's a collection of things, and each of these probabilities are added to each other for this event. The probability of an event is the probability is the sum of probabilities of the elementary events that define it. So we flip a coin, 2 heads, 2 tails. The probability of that is going to be equal to the probability of heads, tails, plus the probability of heads, heads, tails, tails, plus the probability of, tails, tails, heads, heads, plus extra stuff. And so the probability of seeing this event grows. It's bigger than the probability of all heads. Because the probability of all heads is just one single event, or one single elementary event. But the probability of 2 heads, 2 tails, there's different ways that you can make that. And so all of them add up, and that becomes the probability of this event. Fine. So, definitions. Probability space. Definition. An event. A definition. A joint probability space is also a definition. There's no room for creativity. You just do it. You go over what the definition says. Independence is something that also has a definition. And conditional probability is a definition. So when you're given knowledge about the world, then the probability of things happening can change. Because you have information. You have more information. Some probabilities go up, some probabilities go down, some probabilities go down to 0, because these things cannot happen at the same time. Whatever. Definitions. Here, Bayes' theorem, we reach our first theorem. We're out of the world of definitions. And now we use the definitions to show that a statement is true, given all of the definitions that we have. Here, Bayes' theorem is this. The probability of A given B is equal to the probability of B given A times the probability of A, all divided by the probability of B. Theorems need proofs. A proof is using your definitions and things that already exist to go step by step by step to come to the conclusion, which is the theorem itself. So this is a proof of Bayes' theorem. There could be more, but this is one. It's a short one. And fine. Bayes' theorem is really, really important, and it's really useful. In fact, there's another, we're watching this how long ago? There's another YouTube video, I'll try to find it and share it, about when Bayes' theorem has been used in real life to do things. In this 3 blue, 1 brown video, he gives one example of a ship, a boat, that had a bunch of gold on it, like 120, 150 something years ago. There was a boat with a bunch of gold. It was hit by a storm and it sank. And in the 1980s, there was a group of people who used Bayes' theorem to try to figure out where the boat sank. And they found it, and they made like $700 million, because that's how much gold was on the boat before it sank. And it was nothing fancy, just Bayes' theorem. That's it. Like, just Bayes' theorem, how do you search in an area? Is this the location of the boat, given the weather patterns, given where we've seen it before, or where we've looked before, and blah, blah. So, that's one example of Bayes' theorem. The last class we talked about what's actually called the Monty Hall problem. It's named after a game show where people would guess where there's $1 million, behind which door. There's 3 doors. Take your guess on where the $1 million is. Is it door number 1, number 2, number 3? I rephrased it in terms of knights and dragons and caves, but the name for this problem is the Monty Hall problem in probability. And you can use Bayes' theorem to come up with a strategy. Given some knowledge, do you change your mind? Yes. Yes, you should. It's a surprising thing for lots of people. It was a surprising thing for me the first time I learned about it. It's also demonstrative of the fact that people are bad at probability when things get even a tiny little bit complicated. But anyway, I think I talked plenty about that the last class. You can use Bayes' theorem to defend a good strategy in this situation. All right, so we have definitions. We've run into a theorem. We've shown what a proof of a theorem is. And fine. This is a way that Bayes' theorem is also talked about in terms of having a hypothesis given some data. This is more of a approach from hard science. Physicists, chemists, computer scientists, engineers, climate scientists, choose your poison. They have hypotheses. They try to make claims or predictions based on data, and all of that is happening pretty much just through a basic application of Bayes' theorem. All right. Disjoint events. This is another definition. Events that really have nothing to do with one another. These are not independent. Disjoint is not independence. In fact, disjoint events are the most dependent types of events that exist. I won't go through all of that again. All right, yes. And then we talked about this, the law of total probability. And if you watch this 3 blue, 1 brown video on Bayes' theorem, he mentions, let me see, probability of A given B is equal to the probability of B given A times the probability of A all over the probability of B. So that's the definition of Bayes. And what this guy says in this video is actually this, the probability of B, it's usually not that easy. As we saw last class in the Monty Hall problem, the probability of this denominator part was actually the hard part. And in this video, he says actually the probability of B is usually calculated as, for example, the probability of B given A plus the probability of B given not A. This thing means not. And yeah, so you calculate the probability of this thing here. You've already calculated it. If A is true, then what's the probability of B? And then you can also calculate the probability of B if A is not true. And this here is the law of total probability. This is a particular way of, let's see if I can center this. There we go. This is a way of shattering. I'll use the word shatter. Like you take a glass or a plate and you throw it on the ground and it shatters into pieces. Well, you can pick up each of the pieces and add them together to figure out how big the plate was or how big the glass was, whatever. So this is one way of shattering B, which is A and not A. But sometimes you can shatter it in a different way. In fact, when we talked about the Monty Hall problem, when we broke it into pieces, we came up with 3 pieces. These 3 pieces were based on the cave that the wizard revealed, depending on where the princess actually was. And the princess could have been in one of 3 different caves. And so we imagined what would be the case if the princess was in the first cave, or the second cave, or the third cave. And so we came up with 3 pieces of how to consider each of these 3 pieces by themselves, and to reconstruct this this denominator, what the probability was. All right. So in the video that I shared, he focuses on this, but I want to emphasize that that is just one form of this that's called the law of total probability, which is just that the probability of any event is the sum of other smaller probabilities when you cut it up in different ways. All right. Let me get rid of this. All right. So that's Bayes. We will continue to talk about Bayes today, hopefully. There's another example that I want to give that uses Bayes' theorem that I also think demonstrates the fact that our ideas of probability are bad. This has to do with taking a medical test. You go to the doctor and you're tested for a disease. Presumably you don't want to have the disease. But if the test comes back positive, depending, you shouldn't freak out. Like, yeah, the test came back positive. even though it came back positive, you're probably fine. And that is a surprising thing, maybe. But we can show through the math that we've introduced and everything we've talked about that that is the correct conclusion to have. Don't freak out. You had a test come back positive. Be calm. You're probably okay. Most people who test positive are actually negative. Whatever, we'll get there. I'd like to work through this example. And another shocking thing, I'll maybe emphasize this again when we work through the example. Lots of doctors don't know that. There's also been studies of doctors who administer tests, and they were asked if this test, given these things, comes back positive, what would you tell the patient? And a lot of the doctors said, yeah, I'd tell them they're probably positive. That really sucks. It's an uncomfortable conversation to have. But despite their medical training, which of course they're doctors, they know tons and tons about medical things, how to interpret test results when probability matters is something that a lot of doctors aren't very well trained in. That's a real study that happened. There's a lot of doctors who basically don't know enough about Bayes' theorem. Whatever, they're great people. I mean, doctors, geez. We need them. Let's not criticize them for not knowing everything. In any case, this is another example that I'm hoping to get to today. All right. Expectation of a random variable. Let's go through this. Wait. Random variables. All right. Very quickly, let me repeat everything again about probability spaces. All right. So we're talking about probability. What is probability? It's a very, very new, as in it's under 100 years old, framework to understand or to try to make reliable predictions about uncertain events. A probability space, everything that you need in order to understand what the events could be and how much you might expect them to happen, are defined by these two things. There's a set of everything that can happen, and a function that says for every single possible event, here it's an elementary event, what's the probability of that thing happening? And that's it. Everything probability is built on these two things. Now here, the set is of possible outcomes. What are outcomes of this set? They can be anything, literally anything that you like. It can be heads and tails. It can be face 1, face 2, face 3, face 4, face 5, face 6. It can be music. It can be movies. It can be text. It can be smiley faces and frowny faces or emojis. It can be pictures. It can be anything. Anything you want is the set. Now, how often will this thing of the set happen is the role of the function. But the set, anything you want. If the set is numbers, for example, the numbers 1, 2, 3, 4, 5, 6, fine. The set can be anything, including numbers. But for probability, these numbers mean nothing. That is to say, if you add two of these numbers together, what does it mean? It means nothing. They're just symbols. You wrote down something that looks like a number 1 and something that looks like a number 2, and you want to add them together, you do not get the number 3. It's a random symbol that means nothing. What matters is that the number 1 looks different than the number 2. Replace it with a smiley face and a frowny face. What happens when you add a smiley face and a frowny face? Nothing, really. It's nonsense. So, you can use numbers, but here, in probability, the set of events, when you combine them, if you want to add or subtract or multiply or divide or raise to the power or anything else, it's nonsense. This isn't, it doesn't mean anything. All right. That's probability. Let's come to random variables. Now we're well motivated. A random variable is 3 things. A probability space is a set and a function. A random variable is a set and 2 functions. The set and the function, here, that's a probability space. Exactly. Random variables have inside of them probability spaces, which is why you need to understand probability before you move on to random variables or probability distributions. Same thing. But in addition to the probability space, you have another function, x. What is this function? It takes events and maps them to numbers. Maybe the set is numbers and you map them to the same numbers. Could be. These could be pictures, you map them to numbers. It could be music, you map them to numbers. It could be clips from a movie, you map them to numbers. Whatever. This set, omega, is whatever you want it to be. But the function x takes all of those and assigns them numbers. And these numbers, the numbers that come from x, are numbers. They're numbers that you can add, you can subtract, you can multiply, you can divide, you can... all of the stuff that you can do with numbers, x allows you to do. So you have events in omega, And x turns whatever these events are into numbers. And now you can do fun stuff with numbers, things you learned in, elementary school. Adding, subtracting, dividing, multiplying, all the fun stuff. You can do it now. And that is what random variables allow you to do. Of all of the different things you can do with numbers, one of the most important ones is taking an average. That's called an expectation. All that it is it's just an average. Maybe not grade school, middle school. You have 10 numbers, you want to find the average. Add up all the 10 numbers, divide by 10. That's the average. That's it. That's exactly what it is for the expectation. It's an average. And taking an average is a very powerful thing. Not hard mathematically. It's pretty straightforward. You learned it in, 6th, 7th, 8th grade, something. But what you can do with averages is big stuff. And that's what we're talking about today. All right. So a concrete example of a random variable. Here we have a probability space. Colors. They're not numbers. They're not, what does it mean to add two colors together? We're not painters or anything. Like, don't think about blending colors or anything like that. The point is that adding colors together is nonsense. That's what I want you to believe. So we have a probability space that's a set of colors and the probability of these colors happening. And now we define a function, x. And the function x assigns colors to numbers. And now that we have numbers, we can do things like figure out an expectation or an average. What is the average of a random variable? The average or the expectation of a random variable is every single value, every single number that the random variable can take times its probability. So all of the numbers of the random variable, this random variable can take some number of numbers, and we're going to give each of these numbers a weight. The weight is the probability of the number happening. So in the example of a die can take the number 1, it can take the number 2, it can take the number 3, or 4, or 5, or 6. That's it. Those are the numbers that this random variable can have. How much are each of these numbers weighted? Well, if it's a fair die, then each of them are weighted equally by 1/6. So what's the average? You sum everything up. It's a weighted sum. So this is the sum here, the sigma thing. That's the sum of all of the numbers. But it's not just a sum, it's a weighted sum. each of these numbers have a weight, and the weight is the probability. So you take all of the numbers, you give them a weight. The weighted numbers are lighter or smaller than whatever numbers themselves. And you add them up. You add up the weighted sum, and that's it. That is the definition of expectation. You don't need to be creative. You don't need to be, bang your head against the wall, trying to figure out what this thing is. This is a definition. You just plug stuff in. So here is an example of a random variable that's defined from a 6-sided die that's fair, and you expect the number 3.5. I said it before, but I'll say it again. The expectation is an average over time, if you like. This is one perspective. 3.5 is not a number on a die. A number on a die is 1, 2, 3, 4, 5, or 6. There's no 3.5. But that's the expected value, because if you roll the die 1,000 times and added up all of the results and divided it by 1,000, you're going to get something pretty close to 3.5. All right, so that is the definition of expectation. Expectation, averages, have a lot of really useful properties. One of them being the linearity of them. You can scale expectations. You can scale averages by multiplying a number or by adding different ones together. And everything is easy. You can take out the scale factor and compute the average, and then scale it after you're done. You're correct. You can take the expectation or the average of two things added together, and you can compute them individually. What's the average of one? X. What's the average of the other? Y. After I've computed each of those averages by themselves, then I can add them together. And you're correct. That's the exact same thing. This is a property of expectation, which is super nice. It's super nice. Not everything in the world is so kind. But averages are very kind to you. They allow you to be very, very lazy and doing whatever it is that you want to, being lazy. You got the right answer. That's great. That's great. So this is one property of expectation. Today I'll be getting into another really crazy thing about it, but anyway, this is review. What is a random variable? What is an expected value? Why do we care about it? Just wanting to know what the average of things are. Things can be any particular trial, something really rare can happen. Do you want to consider everything that's really rare? Like, oh man, what goes into that? Probably a lot. You're going to be surprised. How much should you be surprised if something rare happens? So when you talk about the average, well, that's a lot simpler. It's a single number. That's one thing I also want to mention. A random variable is called a random variable because it's a random thing. You roll a die. Can a die be 1? Can a die be 6? A die is not 1. A die is not 6. A die is not 2 or 3 or 4 or 5. A die can be 1 with a certain probability. Without the probability, you're talking nonsense. All right? A random variable, let's go back up here, are these 3 things. X here is defined from omega. And anything that happens in omega happens according to some probability. So x is not a number. X can be a number according to some probability. So x is a random variable. It is not a number. It can be a number with a probability. Expectation, though, is a number. Always. X can be different things depending. As probabilities, I'm not sure. It could be this or that. You take the average, things have collapsed. Now it's a number. One number. Always. That's what it is. Okay. Okay, I think that's enough review. I've just basically repeated myself, I think, for the past 40 minutes or something. I see a question about asking another problem for a probability, or for the random expectation of a random variable. Let me, here, I'll pick something. And we can do this after a break. But during the break, you can think about it. Let me think of something. Okay, let's say I'm a movie buff, i.e., I like movies. Make this bigger. Okay. I go to RottenTomatoes.com to look at movie ratings. Of the top 10 movies, I like 6 of them. All right. So the probability space is movies, movie titles, whole things, whatever. The probability here is 6 out of 10 of me liking a movie or not. Of the top 10 movies in any given month, I like 6 of them. What is it? July? All right. Now it's July. What is the expected number of movies I'll like this month? All right, that's a pretty straightforward one. I think this is not hard, but there you go. This is, it's a real problem. I just came up with it. Think about it during our break. Have an answer. Even better than having an answer is telling me why you have this answer. Why are you right? So that's the problem. And let's take a 15-minute break. So we'll come back at 7:25. Start recording this. All right. So now we have a bunch of letters and a probability function. And these, A, B, C, whatever, maybe they're movie titles, make a movie titles, whatever, for this month, the top 10. Fine. Now, the critical part for this question is the function x. And if you're assigning movie A to the number 1, and you're assigning movie J to the number 10, why are you choosing those numbers?
No specific reason. I thought that was kind of the purpose of a random variable. It's just kind of assigning them numbers, 1 through whatever.
Yes. You do assign them numbers. That's right. Here, though, the reason why you correctly were going through things and then thought, oh no, this number is too big. That doesn't make sense. Let me adjust things to make some number that is more reasonable feeling. The mistake that you made is assigning the numbers that you did. Here, don't assign these numbers 1 through 10. Assign them all the number 1.
Huh.
Because, these, yeah, sure, they're top 10 movies, but is the 10th movie any different than the first or the third or the fifth? All the same. It's just some movie. So we should assign it the number 1. So this you started off correctly. You built the probability space just right. Your way of building the x function is where you took the misstep. So these numbers that you're assigning, because I don't know, they were easy to, I'm guessing. Like I'm dealing with 10 things. Let me use the numbers 1 through 10. It's a natural choice. But that's where you went wrong. They all should be assigned the number 1. Before we continue with the rest of things, are you comfortable with this so far?
Yeah, I guess I get that. I just kind of, in the past example, when you did like the 3D cube, you
Yeah.
kind of I think you did like 1 through whatever it was. I don't know if you did
1 through 6. Yeah.
Yeah, so I thought it was kind of like the same principle where we just kind of, gave it a number 1, 2, 3, 4, whatever.
Yeah, it's the same principle. I mean, we're assigning numbers to things. For the die, the reason why you use the numbers 1 through 6 is because generally if people are playing with the die, it doesn't have to be this way, by the way. It's just that's generally I don't know, like die have existed for a few thousands of years at least, and when people see a side with 6 dots, they assign it a number 6 because that, like seeing a 6, counts for something more. So we assign it the number 6. Here, though, if we were to assign individual movies a number, there's really no ordering here. I mean, there's no reason why the top 10 should be weighted,
Of yours.
movie 1, number 10, number 10. Like, that doesn't exactly work. And it's fine. It's fine to, like, go down that route and calculate things that you think, that doesn't seem right. And that's very good. I mean, you're thinking, you're backtracking because you're using your reasoning, and these things aren't computing. So you go back and you're trying to figure out where the mistake was. All right. Before you did these calculations, and by the way, I love that you did a calculation, because yeah, I mean, that's what I hope people can walk away from this course with, that they can sit down and like do some calculations, um, it, and more than that, look at the result of their calculation and think, does it make sense or not? So A plus on all of that. Setting things up, working through them, getting a number that was uncomfortable, and backtracking. Now that we have this, there's the probability space here. And I'm telling you that, what was the number that you had in your head before you started the calculations? What was the number that you thought, that's the right answer?
Somewhere around 6.
Somewhere around 6. Very good. All right. So now I've given you this part, the x function. And the x function is taking anything and mapping it to a number 1. That's a little bit harder for me to explain, other than the fact that these movies in the top 10 list are not important in their order. So let's just make them all the same. And so I'm choosing the number 1. Let me erase this and tell me, given these things, now you have a probability function, and this function x, how do I compute the expectation?
I would do basically the same things I did before, but instead of 1 through 10, just assign them all 1. So 1 times 0.6 plus 1 times 0.6 10 times.
Yep. And what does that give us?
It's like 5.4, something like that.
I'm going to double check.
Yeah, sure. It's 6.
6. Very good. Yeah. Does that answer make sense?
Yep.
6? Yeah. Good. Yeah. So that's the answer. Yeah, it's 6. You like 6 on average. Now, the whole, coming up with a set, a probability function, and this function x is this sort of tiring exercise to come up to the answer that you can probably just jump to, given this example. Yeah, it takes some practice, and you did some really good things along the way. I think the way that you set up the probability function sounds right on. The way that you set up the x function is different because it takes some practice. So I'll try to give some more examples to emphasize that. But you're doing a lot of very good things like this. It was a success, your thought process. Trying to build something, checking it, going back and revising things. But yeah, where you saw your misstep was a bit wrong. The only mistake that you made was with this function x. You tried going to the probability function and fixing things there to get a number that was more comfortable. But you were actually right. Everything that you did up until the function x, that's where you did something wrong. But everything else is great. Yeah.
No, yeah, that was pretty helpful. The only reason why I was kind of thrown off by the x variable, like where we assign things, is kind of the example where you did like a random cube, like a colored cube, and you assigned it 1 through 6. So I just kind of it was the same process.
Yeah, very good. That's a big mistake. That it's hard because I don't know. I mean, like most probability texts or lectures or things like this, they try to motivate people on probability by using things that are kind of obvious to people. Like I think that what authors or teachers or something are trying to do is to make it seem like I'm kind of teaching you things that you already know. And like, so we'll talk about flipping a coin. We'll talk about rolling a die. And so nothing I'm saying is surprising. I think that that's the wrong way to go about it. I think the right way to go about it is to say that there's a mathematical framework that defines probability. And let's motivate it by taking things that you know. Flipping a coin, rolling a die, especially when they're fair. Nothing's hard about it. But the thing to take away from it is that the math is justified. That's it. That's the goal. I don't know, like, people aren't introducing some type of crazy math where you're having to, like, blow up your mind on following things. It's more like, this math makes sense. This is why we define math for this subject, probability, in this way. And for things that you know, we can check that we're not wrong. Like, things that you know are right follow from this math. And that's the right way to think about it. After that, now that the math is established, that it works, then when things get harder, use the math. Because we've already established that the math works. So I feel a little bit conflicted about, I mean, I do the same thing as basically everybody else, I think. When I talk about probability, I talk about coins and dice first. Maybe playing cards, you know. But the only use of talking about those things is to get you to accept that the math is reasonable and to take things that you already know and to go through a different set of steps to get to the same answer that you know is right. The goal of that being that now we have the math and we can use it in all kinds of separate situations. All of, flipping coins, rolling die, playing with cards. The only reason why we talk about that is to get you to accept that doing these things step by step gets you to a reasonable answer. And after that, forget everything that you think about the other stuff. And just now we have the math and we use it, we have it, and we use it. And that's it. So it's a little bit difficult, on the one hand, trying to motivate why these steps exist. It's easy to go to these really visceral understandings of things, but they lose their usefulness pretty early on. I mean, past anything that's just like super basic that, I mean, why are we talking about this in university? Like, I mean, I can talk to a 10-year-old and they know how a coin works. They know how a die works. So why are you here, like, shelling out large sums of money to learn about the stuff in college? And this is the jump. It's not using big words to talk about things that you already know. It's introducing you to new techniques that are justified by things that you know. And now that you're comfortable with these things being justified, because you can use your like basic 10-year-old logic to see it, that yes, I agree with that, to now apply it to bigger things. That's why you're, I don't know, 20-something, and we're talking about flipping coins and rolling die. Yeah. So, yeah, I mean, again, I'm sorry that I myself haven't come up with a better way of introducing these things than everybody else before me, flipping coins, rolling die, playing cards, but, uh, anyway, maybe I'll think about it still. This is why I think that people go through these motions, and that I myself am also falling into the same patterns. But my goal for this course and for our time together is to get you to feel comfortable with some simple tools of how to think and how to work through things when they get complicated, which is most of the time. Most of the time, the world's not nice and simple. But when things get complicated, sometimes you can actually, describe what are the events that can happen. What are these probabilities? What are the numbers that I'm going to assign to them? And all of that is the hard part. But once you do that, hey, everything's great, you just got this whole step by step, bring out your calculator, open up Excel, have it calculate stuff, and you know what these numbers mean and all of that. That's the point of me teaching this course and what I'm trying to convey to you, all of my students, for the 5 weeks we have together. All right. I feel like I've just given a really long diatribe. Sorry about that. I hope it's been helpful. Okay. Let me cut off my camera again, and I'm going to show you a program that I put together. And after that, we'll take a break, and we'll delve into this program that I wrote and what it shows, how it can motivate bigger ideas that we'll talk about. Great. I think this should be shared. Can I get some confirmation in the text box that you see a new screen with Jupiter at the top? Yes, great. All right. So this is Python. I know that a lot of you guys don't know Python, or maybe aren't interested in Python at all. I think there was exactly one student who was interested in Python, so I'm not going to talk a bunch about the code itself, other than to say this is a program called Jupiter, spelled with a Y here. This is Python is a computer language that is far and away the most popular and the most widely used in the United States for about anything you can think of. It's a very old language. It was made 20, 30 years ago. And if you might be interested in learning anything about programming, Python is the place to start. It's very old. That means that it's very stable. It's been looked at, and there's been lots of contributions to it. So a lot of the things, even on your most creative days, that you might think about wanting to do, probably somebody else has already done. And so that makes it easy. You can just take the things that other people did and import them. That's this. That's this first thing. Import. Let's take things that other people did and use them. So Python's a very good programming language, worthy of your time, more than any other programming language, unless you have some very specific reason. That being said, this isn't a programming class. You guys aren't developers, but insofar as that I'm showing you stuff using Python, maybe you want to learn it at some point. Now you know a little bit more about it. So here, these import statements are taking code that other people wrote, and I want to use it. So that's what these imports are. NumPy is a thing for building arrays of numbers. Here we have a plot library. It's like we want to visualize things. Draw a picture to see stuff. That's what that is. Seaborn is putting things on a plot in a pretty way. Let's make the plots look pretty. That's it. All right. So, Jupyter Notebook, this thing. Let me say something quickly about this. This is a program where you can write Python code, and you can also make notes to yourself about it, or anybody else who's reading it. You can, like this thing, it looks really big lettering. Put a big number sign in front of it. That will make it look big. These things, I'll number them in this way, and hey, there we go. Things look pretty. Very nice. Besides writing text and making it look pretty, you can also write Python code, and it will run the code inside of your browser. So here's a browser. It's Microsoft Edge. Nobody should use. It's horrible. But in any case, I don't know. I don't care. Whatever. Let's not go there. So it's a combination. This Jupyter Notebook is a combination of writing text and Python code. And this Python code you can run by itself. So like this little box here, this little bit of Python code, I can run it by itself. Now it's been run, it's been executed. And it can display results to you in your browser. So it's a really nice thing to work and to keep track of stuff that's going on. Here is, I'm just defining variables. So here's a variable called numTrials. I'm assigning it the value of 1. Here's a number n. I'm assigning the value of 10. And a probability. that I'm assigning the value of 0.5. Here is a function. In Python, you define a function with the def. That means I'm defining a function. This is the function name. And this is what I'm passing into the function. So I give the function something, and I'm going to get something back. Here, I'm going to be getting back the number 1 or the number 0. And I will get the number 1 if, when I generate a random number, it's bigger than some probability defined by this number p that I give the function. So I tell you, this is how much the coin is weighted. Here it's a fair coin. So generate a random number between 0 and 1. If the number is bigger than, in this case, 0.5, return the number 1. If it's smaller than 0.5, return the number 0. But I could have a weighted coin. I mean, I could make this, 0.9. Ooh. And if I make this a weighted coin, then what this would say is generate a number between 0 and 1. If the number is bigger than 0.1, 1 minus 0.9. If it's bigger than 0.1, return 1. Otherwise, return 0. So given this value of p, 0.9, when I call this function, 9 times out of 10, I will get the number 0. Otherwise, I'll get the number 1. Let's make it a fair coin again. Okay, so that's quick stuff about Python. We have a definition. Here is a for loop. A loop is something that exists in basically every programming language. What a loop does is it says, do this thing again and again and again and again and again and again until stop. So what this says is do this thing 10 times and then stop. And print, show me the number of this function. Here, Bernoulli 0.5 is calling this function. That's calling a fair coin 10 times. Let's see what it looks like. There we go. We flipped a coin 10 times. Tails, tails, heads, heads, tails, heads, heads, tails, heads, heads. Cool. Do it again. Heads, heads, tails, tails, heads, tails, heads, 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 tails. All right, well, do it again. And there we go. We can do this a bunch. As many times as you like. Oh, look, this time we got 2 heads. That's it. Oh, that's kind of rare. Interesting. Okay, do it again. Most of the time, you'll see 5 ones, 5 zeros. All right. So now this is computer code flipping a coin a bunch of times. All right. So here we define a coin flip. Here we're saying we're going to flip the coin however many times, and let's look at the heads versus tails. And you can do it as many times as you want. This is called a simulation. And we're having a computer do stuff for us. Okay. Next up, we have this binomial distribution, and let's talk about that next. For right now, we'll take a break. I will leave this Python code here for you if you're interested. Take a look. It's not, I hope it's not scary. It's certainly something useful to know. But if you hate it or you're not interested, no problem. I wrote this code to talk about concepts for this class. This is not a programming class. If you forget, if you don't care, forget about all of the stuff. Just look at their results. Look at stuff that's printed. But these things aren't hard, and they're accessible. So let me stop there. Let's come back at 8:25. 50 minutes. All right. See you guys soon. And we're back. Great. Okay. So again, this is a Jupyter notebook. Jupyter is a web server that runs a web page where you can have text and you can run Python. This is not a programming course, and I don't expect you guys to know or even to be interested in anything programming. That being said, there's been at least one student who said that they're semi-interested, so I'm trying to make things not horrifically not understandable. All right? So whatever we import stuff, because Python has existed for a long time, let's not code these things ourselves. Let's use other people's things. Let's define stuff that we want to use later, including a function. And here is a loop, where a loop does something over and over and over until you tell it to stop. In this case, I want to run something 10 times, and after 10 times, stop. What do I want to happen 10 times? This function. Flip a coin, a fair coin. Do it 10 times, print the result. That's the print. Show it to me. Ones are heads, zeros are tails, or vice versa, whatever you want. So you can run this over and over and get different results, and here's a bunch of different results. Who cares? Now, this is a Bernoulli function. Bernoulli is the name of a guy who came up with the brilliant idea of flipping a coin that turns up heads or tails. Smart. Cool. So Bernoulli came up with this idea. Now we're in the late 1800s, maybe mid 1800s, I should check. Whatever. And coins are not always fair. A fair coin with a 0.5 probability is heads or tails. Maybe you have a trickster who has weighted their coin, and they're going to make the coin, let's just do it. Let's do it, because that's the power of programming here. Let's weight our coin, 0.9. What this means is that 9 times out of 10 is going to be tails. What happens? Look at that. Oh, tails every single time. Or heads, whatever. However you want to assign a 1 or a 0. Look at that. All right, how about another time? Okay, now we get some differences. Do it again. Sorry, here. Different results, but a bunch more ones than zeros. You can do it a bunch, as many times as you want. Hey, thanks, programming. Whatever. We can run 10 flips of a coin in a second. Fine. So that is the Bernoulli function. All right? Flip a coin some number of times. Now, let's move on to the binomial distribution. And I've heard about this. I've heard some students use this word, a binomial distribution, and I haven't talked about it yet. And congrats for everybody who knows something about it. But in this course, now is the first time that we are seeing this. A binomial distribution. A binomial distribution is built on top of a Bernoulli distribution. A Bernoulli distribution is flipping a coin one time. Once. That's it. A binomial distribution flips a coin. You see two things here, two numbers. P, that's the weight of the coin. 0.5 is a fair coin. Anything else is a weighted coin. N is the number of times you flip the coin. And what a binomial distribution counts is the number of heads. You flip a coin n times, and out of these n times that you flip the coin, how many times did it show up heads? That's it. That's a binomial distribution. So in code, a head is called a success. And this is something called a list compression, whatever, in Python. The brackets here are a list. And in this list, we're going to call this function, Bernoulli, this many times. And every single time we call this function, we're going to put that thing in a list. So this is Python specific. This is called list compression. Whatever, if you care about Python, cool, that's something Python does. If you don't worry about it. What this function does is it returns, you say I'm going to flip a coin that's weighted with P, and I'm going to flip the coin n number of times, and then I'm going to count how many heads I have and return that back. That's it. All right. So, whatever, I won't go through this because this isn't a programming class. All right, here we go. Now, here is a very important step that we're taking today. Before, let me go back to our notebook. Not this. This. Here we go. Expectation. Let's compute an average. We have a random variable. The random variable is random. It's not a number. The random variable is not a number. It can be a number with some probability. Now, let's compute an average of this number. The average is a number. It's a number. It's one thing. Not probability. Probability is gone when we're talking about averages. Probability, with an average, everything collapses to one number. Okay. This expectation is a mathematical concept. What do I mean by a mathematical concept? What I mean is that this is a definition. You can't play with it. There's no room for creativity. It's something that is being given to you, and you just do it according to the definition. When you follow the definition, in this case, you get a number. End of story. Now, this is in a perfect world. All right? So, when I was saying, what is this 3.5? Like, what is this number? First of all, it's not a number on a die. You don't see 3.5. So what does this number mean? That it's the expected value. Because you never see it. But it's the expected value. Well, what it means is you do this thing over and over and over, and you take an average over many, 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 many trials. What is many, 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 many? It's infinity. You do it forever, and you take the average over forever, and this is the nice, clean number that you'll get. All right, this probability of 1/6, what does this 1/6 mean? This means you've done this experiment infinity times, and this is the ratio that you see the number 1. Now, you might take a die and you can throw it and you can actually count how many times the number 1 shows up, and you might not get 1/6. you'll get something close to it, especially the more often you throw the die. But you probably won't get exactly 1/6. It'll just be something close to it. The more you throw the die, the closer it will get. You throw it an infinite number of times, bam, there's a 1/6. All right, so this is an idealized world where you're doing something an infinite number of times. Okay. So that's an abstract world where you have an infinite number of trials to do something and to calculate a number. That's not the world that we live in. All right, we can imagine it, and we can imagine where things go, and we can get to the 1/6, and fantastic. Here we are. But this is us going into some abstract world where we can do something an infinite number of times. Okay, let's go back here. Here, what we're doing is we're not playing with infinity. All right, we don't have that luxury. We're living in a real world where we do something some number of times. And given the number of times we do it, we stop at some point. Like, we're satisfied. It's close enough. I've done it enough times. Now I can estimate, what does infinity look like? Maybe you're a mathematician and you don't need to do simulations on a computer, and great. We're not mathematicians. We're in the business school. And we can do things some number of actual times. What this does, this function, we flip a coin. It's a fair coin. 0.5 is the probability of heads versus tails. This is a fair coin. How many times are we going to flip the coin? 10 times. That's how many times we flip it. 10. Great. We flip a coin 10 times. We count the number of heads. Done. Now, let's do that same thing more times. 5 times. This 5 means we're going to flip a coin, a fair coin, 10 times, and we're going to do that 5 times. So 50 coin flips altogether. Flip it 10 times, count the number of heads. Flip it another 10 times, count the number of heads. Flip it another 10 times, count the number of heads. We do that 5 times. How many heads do we get? That many. The first time we flipped it 10 times, we got 3 heads. The second time we flipped it 10 times, we got 4 heads. Then we got 7 heads, and we got 7 heads. Okay? That's it. Let's do it again. There we go. We flipped a coin 10 times, 5 times. We got 4 heads, then we got 4 heads, and 4 heads, and 4 heads, and 6 heads. Cool. Do it again. Different. Okay, now we got 7 heads, and 4 heads, and 5 heads, and 5 heads, and 6 heads. All right. Now, the thing that's happening here, I don't know if it matters, but whatever. Maybe seeing me makes a difference. I don't know. This is an important step that we're taking, okay? There's an expected value where in one trial, we're talking about a joint probability space here. In this case, this joint probability space is 10 times of flipping a coin. Sorry, that's a 10. We flip a coin 10 times, and that is one trial. Now, we flip the coin 10 times, 5 times. Okay, this is a big step, actually, that we've taken doing this. You flip the thing 10 times, or whatever number of times you want. How many heads are you going to see? What's the expected number? Well, it's going to be half, right? I mean, like you flip a coin 10 times, you expect to see 5 heads on average. On average here means when you do the thing a bunch of times. Now, what we're doing is calculating an expectation empirically. This isn't pure math. This is running an experiment, trying to estimate it. Maybe our math isn't so good, and we can just do it on a computer and count on a computer. And when we do it enough times, we get an okay whatever amount. The important step that we've taken is that we're calculating an expectation again and again and again and again. So there's a single coin flip, there's many coin flips, and then there's many trials of many coin flips. Okay? Like we're stacking things. And that leads to something very new and a new territory that we are going to be in. Let me run this experiment a couple more times, and I'll repeat myself what it's doing. Here. We're flipping a coin 10 times. It's a fair coin. 50% probability of heads and tails. We flip it again 10 times. How many times do we flip it 10 times? In this case, 5 times. And then we count the number of heads. So we flip a coin 10 times, we count the number of heads, and all of these times. This time, we got 5 heads on the first 10 flips, 6 times on the second 10 flips, 6 times on the third 10 flips, 4 heads on the fourth 10 flips, and 6 times on the fifth 10 flips. All right? So we have a coin, we flip it a bunch of times, and then we do that thing a bunch of times, over and over and over. that is the, this is doing a binomial distribution many, many times. Now, for any of these 10 times, why do we have 5 and 6 and 6 and 4 and 6? Because we expect the number 5 each time we do it. These numbers aren't so far away from 5. They're not 1, they're not 10. Could happen, but not often. Most of the time, every time you flip 10, a coin, a fair coin 10 times, it's going to be something around 5, probably. So now we are taking it, we're seeing, what we're building up to is taking an average of averages. Okay? That's the layer that we're doing. There's an expectation, there's an average. But when you compute the average, or you estimate the average, or you do an experiment to calculate whatever it is, the average, do that same thing over and over and over and over and over. And now, take the average of the averages. Okay, that's what we're building up to. So here, again, I'll run this a bunch of times. Notice that we don't get the number 1, we don't get the number 10. Or if we do, we don't get it very often. Basically, the number is around 5. Okay, I can spend a long time running this. What you will notice is that most of the time, we get something that's close to the average. Okay, so there's an average of averages. That is a very big leap in sort of not psychological, philosophical. It's a philosophical leap. Not just considering an average, but when you take an average and an average and an average and an average, and of those all together, take the average of them. That's a big thing. That's big stuff. That made people famous a couple hundred years ago. And that is what defines a bell curve. That's what will bring us into a continuous probability realm. And that's the only continuous probability thing that we'll talk about in this course, is a nice, smooth bell curve. We'll spend more time today, I think, building up to it, and our next class for sure, understanding it a bit and stuff. But for now, the steps that were taken to get there were exactly this. There's a binary thing that can happen, and it doesn't even have to, actually, it doesn't have to be binary. That's also very cool stuff that we'll talk about. But for now, think about a binary coin flip, okay? It's a coin. You flip it. You flip it some number of times. You flip it enough times, you'll estimate how weighted it is. If you flip it n times, if you get n over 2 heads, that's a fair coin. If you get n heads, oh, that's a weighted coin. Like that coin has something funny going on. You get 0 heads. That's also a weighted coin in the opposite direction. But you flip it a bunch of times and you can estimate how weighted it is. Okay. Now do that again and again and again and again and again. And flip it n times. And then do that a bunch. And every single time you do it, record the number of heads and compute the average of the average. And we're in business. We're in an entirely new area of, this is a defining moment in statistics. It's basically the single most important conclusion of physics, or not physics, of statistics, and this is what we're building up to. So please think about that. Let's take a 15-minute break. Grab some water, a coffee, I don't know, whatever you do with your time. But averages of averages. Soak it in for a few minutes, and we'll pick up in 15 minutes. Thank you, and talk soon. We're recording again. Great. All right. Here, I'm going to pick out on a couple of you to help me out. Don't worry about this Python code. The only 3 things that you need to worry about are these 3 lines, okay? The first line, the weight of the coin. The second line, how many times we're going to flip it to try to figure out the weight of the coin. This third thing is how many times we try to figure out the weight. All right? That's it. Don't worry about all this other stuff. If you're curious, you want to know whatever, reach out to me. I'll explain it to you. But for the purposes of this class, this lecture, look at these 3 lines. All right. Let me try this one time before I pick out somebody. I'll make it a fair coin. What? Oh. Really? Sorry, my keyboard is not behaving. There we go. We'll keep it to what we did last time. All right? It's a fair coin, 0.5. We flip it 10 times. We do that 5 times. What do we see? This. All right. So we got 5 heads 2 times. We got 6 heads 2 times. And we got 7 heads once. All right. So there's 1. That means 1 time we did this. We got 7 heads. 2 times here. we got 6 heads. 2 times, we got 5 heads. All right, try it again. There we go. 4 times, we got 4 heads 3 times, 5 heads once, 6 heads once. All right, so that's what this thing produces. All right, we flip coins, we get stuff. Don't pay attention to this curve. That is irrelevant. I'm sorry I didn't prepare enough to erase it. By default, it shows this. Ignore it. What we care about are the bars. Here we got what is this? 3, 4, 5, I guess, and 8. Anyway, all right. Now you have, hopefully, an idea of these 3 numbers that we care about and the bars that they make. So let me pick out on Daria. Hello.
Hi,
Hey, how are you?
I'm good.
Which of these numbers would you like to play with?
Maybe the number of times we play the game.
Okay. Now we're playing it 5 times. How many times do you want to play?
50.
How many?
50.
50. All right. Before I run this, what graph do you think is going to happen?
I'm a little confused by that question.
Okay. So I'm not running this code yet. This code is going to draw a graph. And these are the 3 numbers that define the graph. So we have a fair coin. We're going to be flipping it 10 times. How many times are we going to flip it 10 times? 50 times. So what kind of graph would you expect? Where on the x-axis, this is the number of heads that you'll see. And on the y-axis is how often you will see so many heads.
So my guess would probably be that it would become like closer to like 5, like it would become more of a, I don't know how to phrase this.
We're getting in complicated territory. So the fact that you're not like an oracle, like that you don't have a good answer, it's fine. Especially because, oftentimes, at least if you program, you try it and you see, and you explain it afterwards. But for now, just for fun,
I just would assume like the more times we play the game, the
Yep.
times where like both of them would be. So like the closer it would become that the amount of heads and tails would become like more of the same number.
Okay.
So I don't know exactly like how that would change the shape
Yeah.
of the graph.
Mhm.
But I have like a understanding of well, I guess the numbers would look like once we like ran it.
Very good. Okay. Thank you for your prediction. I will run it. We'll see what happens, and you can explain it to me. All right? There. Let me go down. There. What are we looking at?
So it did become steeper, and the values did seem to move closer towards um the middle, I guess.
Yeah, so this big thing in the center. What is this? First of all, what number does it correspond to?
I think 5.
5. Why 5?
Um, like
You flip a coin 10 times, and you count the number of heads. It's a fair coin. You play this game 50 times. You see a big thing around the number 5. So what does that mean?
well, that the most frequent amount of times you got it was 5. Of the same.
Yeah. Why isn't there like 0 here? Nothing. Here, 10. Nothing. Why? Does that make sense? Or is something maybe
Well,
the code is wrong, or maybe this is fine. Yeah.
well, it's a fair coin, so I would assume that it would have to land at least probability-wise a certain amount of at least like once or something on like each side.
Yeah. What would if there was something here at 0 and there's nothing that is at 0, but if there was, what would that mean if there was something at 0?
Wouldn't that mean like the coin didn't flip?
No. A 1 is heads, a 0 is tails. And we're counting up to 10. We're flipping a coin 10 times. So a 0 would mean, for example, all tails. That is, we have 0 heads out of 10 flips. Would it surprise you if you flipped a coin 10 times and it was tails every single time?
Oh yeah, if it was a fair coin, then I would expect to get some heads.
Yeah, that would surprise you. Okay, how about getting all heads given a fair coin?
It'd be the same thing, just in the
Yeah, you're probably not going to see it, right?
Yeah.
no matter how many times. I mean, we played this game 50 times, where he flipped the thing 10 times. Out of these 50 times of flipping a coin 10 times, 0 times that we played the game did we see all tails. Also, 0 times that we played the game did we see 10 heads. Are you comfortable with this graph? Is there something surprising to you about it, or it's kind of what you might expect?
I mean, it's what I expect because the most amount of times was what, like, the probability of getting closer to it being very fair. So 5 being head, like the same amount of heads and same amount of tails. So I would just expect it to go closer and closer to that, like the middle to become steeper and steeper the more times we play it.
Very good. Yeah. You play this game 50 times. You might put money on the table that you will see 5 heads, 5 tails. And this, if you put money on the table, is how often you would be right. 40% of the time. This time that we played the game 50 times. Very good. Thank you, Daria. Let me pick somebody else. How about Inari? Okay, how about Kyle?
Yes.
Hey, I want you to change one of these 2 other numbers. We're going to play this game 50 times. But you can change the weight of the coin, or how many tries we have to guess the weight of the coin.
We could do the weight.
Okay. What do you want to change it to?
Do like 0.9.
0.9. Very good. Okay. What do you expect to happen before I run the code?
Well, that's so it would land on. There's like a higher probability that it will land on what would be heads.
Sure. Okay, and how will that make the graph look?
It's gonna shift from like the 0.5. I think there's going to be more in the direction of 0.9. Like for on the x-axis, it's going to shift closer to 9.
Very good. All right, let's try it. Okay. Do you agree with that? Is there something wrong about this, or is this what you expected?
Yeah, I would say it's what I expected. Other than the 6 kind of throws me off a little bit, I think. Just because it's a lot lower with the weight.
Sure. Yeah. I mean, but still, like, you never fall. I mean, you never get 5 tails. Right. Yeah. And in fact, just, this is one trial. In fact, you can run it a few times and see more stuff. I don't know. Here's a few more trials. Again, don't pay attention to the curve. That's I should eliminate it. But very good. Yeah, your prediction, I think, fits. Yeah, very good. You predict something, it's roughly what we see. All right, thank you. Yuhi.
Yes.
Okay, you are going to round us off. You are going to close off our class. You have the ability to change our last remaining number. We're going to stick with 0.9. We're going to play the game 50 times. But now, each time we play the game, we have a certain number of flips to estimate the weight of the coin. That's the number that you can play with. So, how would you like to change it?
Can I get to like 10,000?
Oh, very good. That's a big number. I like that. That's 100,000, 10,000. All right. Now, what do you think will happen?
I don't know. Maybe the graph maybe more spread. Like
More spread. Okay. What does that mean? More spread.
I don't know how to explain, but maybe we will get a more smooth curve.
More smooth curve. Okay, sure. All right, let's see what happens. Oh, it's taking a while because you picked a big number. The coin's flipping a bunch right now. We have to wait. My computer's not that powerful. It'll finish before class. We'll see the graph, you can explain it, and then we're done. Oh boy.
Maybe I should just choose a smaller number, sorry.
No, I like the ambition. Sure. 10,000 is a good number. Yeah, let me give it another 10 or 15 seconds. If it's not finished by then, we can adjust. Here we go. All right. Is it more spread?
Wow.
Okay. What does this mean?
Well, that basically means they're most of the time it just appears the head.
Yeah.
So you just get more concentrate on what we expected on the success rate.
Okay. So every time we want to measure the weight of the coin, we're going to flip it 10,000 times. This is a coin that prefers heads 90% of the time. So here, 9,000. 9,000 out of 10,000 times, the coin lands heads. Not surprising. This is another one that is also equally as high, but this, how far away is this number from 9,000?
It's not that far.
It's not that far. Do we get 1,000 heads? How about 5,000 heads? Or anything less? It's not even on the graph. Like, that's probability 0 for how many times we've played this game. Like, everything is very, very concentrated around 9,000. Does that make sense to you?
Yes.
Yeah. You would be surprised to get 5,000 heads flipping a coin 10,000 times that prefers heads 90% of the time. Okay, great. Thank you so much, Yuhi. Those are our 3 numbers that we've played around with. Guys, I appreciate you listening and participating in this lecture on a Thursday night from 6 to 10 p.m. Oh boy. I hope that you've learned something. I hope that we will continue this. The binomial distribution is the foundation for our first continuous distribution, which is the only thing that we'll talk about for continuous distributions, which is a nice, smooth bell curve that you can analyze with calculus, but this isn't a calculus class, and so we won't talk about it. But the motivation is coming from this. So the binomial distribution is built on these things. You have a coin, you flip it a bunch, you count the stuff. You count the number of heads. That's it. We've tweaked each of the 3 numbers and saw how stuff changes. If you're interested in this, I'd be happy to share this code or this webpage with you where you can play with things on your own. Otherwise, thank you for listening, and I look forward to seeing you guys next Tuesday. Have a very good weekend. Thank you very much.